So we've seen how to show the consistency of the axiom of choice in Gödel's construction of the universe L. So the order of the construction of that universe was so uniform and so nicely defined that meant that we could define a well order of the whole universe. So there's some evidence that Gödel had thought of another way of showing that the axiom of choice was consistent, using a different, possibly inner model of V. And this is called the hereditarily ordinal definable sets. It's not entirely clear what Gödel wrote some hints that he could prove or justify the AC by showing that it was true in such a universe. But he never actually wrote this down. And also it turns out that to do this properly, you have to have the reflection theorem. Well, the Montague-Levy reflection theorem wasn't proven until 1959 or 60. So other people have read this as saying that in fact Gödel was quite aware of the reflection theorem, except that he hadn't written it out, which is indeed quite conceivable for somebody who thought so much about the universe V. So what we're going to do now is look at first the ordinal definable sets. These are those that we can define just in the whole universe of V, but from ordinals. So we look at a set X perhaps, and there's an ordinal with free variables V0, V1 up to Vn. So that I put in ordinals for V1 up to Vn, and there'll only be one set X that will make this formula phi true with those ordinals. So we'll say that X is ordinal definable. We'll then look at the whole collection of these sets, ordinal definable in this way, and investigate these. And eventually we'll see that not exactly the ordinal definable sets, but the ones that are hereditarily ordinal definable, meaning their members are ordinal definable and their members are ordinal definable and so on. This class will be a model of ZF with the axiom of choice. But that's a little bit further in the next lecture. So today we'll just introduce the notion of ordinal definability. And we came close to this when we were defining the def function. So preliminary to this, we'll define the OD star sets, ordinal definable star. This is only just standing in. It's a placeholder for the true definition that will come a little bit later. So we'll go back and look at the def function again once more. So this is in the end of section 3.4, page 48. We're going to define something as being outright definable according to the definition in exercise 3.6. So definition of being outright definable. And this is in exercise 3.6. So we're going to say that X is outright definable. Set X is outright definable if, we'll say that a set X is outright definable in a structure Z epsilon. If there's a formula phi with just the free variable V0, so this is the only free variable that's in there, is V0. So that X is the only set so that Z epsilon thinks that the evaluation where I put in X for V0. It's the only set that makes the formula phi come out true in Z. So to put it another way, the singleton set X here, if I write this, look at the collection of W's in Z, such that Z epsilon W for V0 here, there's only one W that makes this true, X. So it focuses, this definition focuses just on this one set X. It's the only thing that makes it true. So we'll say that def 0 of Z is the collection of these singletons X that we can define in this way. So that X equals this here. For some phi. With the free variables of phi being just V0. So we let phi vary, and we just see for some of these phi's, they'll define nothing. Some will define more than one W. Those we aren't interested in. What we're interested in is the phi's that define a unique set. We collect all those unique sets together as phi varies, and we call these def 0 over Z, definable using 0 parameters. Then definition 320, we say that a set X is ordinal definable star or just OD star if for some beta X is outright definable over a V beta. Right, so we're allowed to look at different V betas and see, looking at the possible, countably many possible definitions, because there's only countably many formulae with V0 free, which formulae define uniquely an X. So the collection of all of these X's is this class OD star. And it is a proper class. So example, every ordinal is OD star. Because suppose beta is an ordinal, then what is singleton beta? It's the collection of W such that, and now I just look at V beta plus 1 epsilon. What's it going to think? It's going to think W is the largest ordinal. So I'll write out a formula that says V0 is the largest ordinal, and I look at the W's that make this true. Well, this works because the ordinals of V beta plus 1 are precisely beta plus 1, and that's got a largest element, beta. and there's only one largest element, beta. So as I let this beta plus 1 vary, I pick up all of the singletons beta, right, using this formula. So every ordinal beta is OD star. Any V beta itself is OD star. You might like to think about different things that can be OD star. Well, singleton V beta is then the collection of W's such that V beta plus 1 thinks there is some gamma such that W equals V sub gamma, and gamma is the largest ordinal. See? Simple, right? Because again, the largest ordinal in here is just beta. So this is saying W will make this true if W is V beta. And it's the only thing that will make it true. Hence, it's a singleton. So every V beta is in OD star, and every ordinal is in OD star. And there are plenty of other things in OD star as well. So, exercise. If X is in OD star, then singleton X is in OD star. Okay, it's a little bit of a, well, not a trick question, it's a perfectly legitimate question. Something is in OD star because singleton X is definable in the way we're talking about. So this says if singleton X is definable in this way, so is the singleton of X. Yeah, so just try it out on beta. Say, check that beta is in OD star. We just showed that any beta is in OD star. This is saying singleton beta is in OD star. And all you have to do is just monkey around with this definition here to get what we want. Okay, so this is preliminary to our definition of the true notion OD that we're interested in. Right? It'll turn out that the true OD we're interested in coincides with this OD star. So now I want to go back to our development. We go back to 4.5, section 4.5. So ordinal definable sets and HOD. So let's see what we have here, 420. We say there's a set Z says ordinal definable. And we'll write Z is in OD. Right, if for some formula phi V0, V1 up to Vm, with these as being the free variables, then for some ordinals that I place in here, so for some formula and for some M tuple of ordinals, now the formula defines uniquely some object. There's only one object that makes phi true if I plug in these ordinals for these three variables, and it's z. And z is the unique set. So again, the emphasis is on one thing that's being defined. Such that phi holds, when I put in z for v0, alpha 1 for v1, etc., alpha m for the mth variable. So for this particular choice of these alphas, there's only one set that makes this true. Okay, so this seems a reasonable definition, but there's some point to be made, is that whereas the def function or the def zero function talks about definability over a structure, we haven't said anything like that here. We're just talking about phi being true in the universe of sets, V. So it's not clear that what I've written down is a definition that I can give in ZF, set theory. Because it talks about truth in the whole universe of E. And if you recall something about Tarski's theorem on the undefinability of truth, that says there's no formula that'll give you a truth definition. But here I am using a truth definition in order to define OD. So actually what I've written here is not yet a bona fide definition within ZF of this concept. But it will be. But we have to work at it a little bit here. So we need to show that Z in OD is in fact definable in ZF. This is too informal up here. So we're going to do a couple of exercises, warming up to the idea of how to show that this is in fact definable. So look at 416. So let gamma vector be this sequence. So it's a set, it's an ordered n-tuple, gamma 0 up to gamma n minus 1. So I think of this as a finite function from n into On. Then what is supposed to happen? For some beta, this tuple is outright definable over V beta epsilon. And now that we get used to this idea, I shall just write V beta in future rather than brackets V beta comma epsilon brackets. Okay. We saw before that any single ordinal, right, gamma 0, say, is outright definable over V gamma 0 plus 1 as the largest ordinal. But this is saying any n-tuple, any finite tuple of ordinals is also outright definable over some V beta. Question is, how do we show this? How do we discover this fact? So solution. So now I'm just writing that point down. We saw before any single ordinal gamma is in def 0 over v gamma plus 1. What we know, the difference here is we're looking for a finite tuple. Here we want this for the finite n-tuple gamma vector. That's what we're trying to do. Well, we'll consider a well order of all possible n-tuples. This actually is defined in an exercise in chapter 1, which I don't think that we looked at. So we'll consider the well order of all n-tuples of ordinals and less than superscript n. And the idea is, here's one n-tuple. This comes before this other n-tuple here, if and only if the maximum of this n many things is less than the maximum of this n many things. Or they're the same. Or they're equal here. But then we look at the least place where the tuples differ. So if I less than n is least such that alpha I is different from beta I, after all, if they're going to be different things, they're going to have to differ somewhere, then alpha I is less than beta I. So one should check that this is actually a well order. Well, I think this is reasonably easy to do, to check that this is a well order. And that's what that exercise asked you to do. And I believe that's in the solutions. Anyway. So we're going to use this to help us out here to show this. And interestingly, what we do here is some version of like Ricard's paradox. You know, the one that says the least natural number, which is not definable in less than 19 syllables. But actually, I just defined it in less than 19 syllables. Right? So this then is supposedly a paradox. So we do the same thing here. We suppose that this tuple here is not def 0 over any v beta. So we suppose there are such tuples. So we let this be the least in this well order tuple that's not definable over any v beta. And then we'll see that we can define it. So let alpha vector be the least n-tuple such that for all beta, alpha vector is not outright definable over v beta. Right? This is what we're trying to show, is that every tuple is so definable. So we've got something here in quotes. So let me call this thing here in quotes, which is about alpha vector. Let's call this phi 0 alpha vector. So I've got here a formula with just the one free variable. And what I put in is alpha vector here for the free variable. So the single set here, the set which is this sequence, alpha 0 to alpha n minus 1. So this thing here, this is, we're going to abbreviate this as phi 0 alpha vector. Okay, so we're assuming that this is true of this alpha vector. I mean, if there are gamma vectors which are not outright definable, there's at least one. So let alpha vector be it. So this is something that's supposed to be true. So by the reflection theorem, if it's true, then it's true in arbitrarily large V deltas. So by the reflection theorem, we have phi 0 of alpha vector occurs in V delta. It's true in V delta. Since phi 0 alpha vector here is assumed true in V. But what have I done here, right? Alpha vector is definable using this well order. It's the least thing which is not definable outright over an EV beta. That's what phi 0 says. So phi 0 of alpha vector here is true in this V delta. But what have I done? Over V delta, I've defined alpha vector. It's the least tuple, n-tuple of ordinals, which is not outright definable over any V beta that's in V delta. So I've just defined it over V delta as this, literally. So this is outright definable over this V delta as, well, and then repeat this statement to yourself. So that then is a contradiction because alpha vector is outright definable after all. So this then here is true. And the exercise is finished. So you may want to think about this move at the very end again, right? And check your understanding that, I'm not trying to pull the wool over your eyes here. Okay, so that's 416. So let's look at the next exercise here. So it's a slightly more complicated statement here on this one, but it's stated so that it's the right thing to say for the theorem that follows. Okay, so this is an application of the reflection theorem due to Dana Scott. So for any formula, what have we got? Psi's here. V0 up to Vm minus 1. So again, implicit in this is these are the free variables, or free variables are contained amongst these. Oh no, it says explicitly. So the free variables of psi are precisely these. It's a kind of omnibus statement now that's coming. It's a conjunction of two things that we like. So the first thing says, for any n-tuple I can find a place where it's outright definable. Well, we found that. That was the previous exercise. So that's not new. But we want this beta to do something else as well. We want it to be a reflection point for the formula psi. We know by the reflection theorem there are unboundedly many betas which reflect the truth of the matter about psi when we put in some parameters. We know that there are betas where we can uniformly outright define this tuple. So we want something to do both at the same time. So, and we want of beta that for any gadgets that we put in here, xm to the minus 1 in v beta, I'll have psi of these gadgets that I put in here if and only if it reflects to v beta. So v beta is a good place. It reflects psi, and we can outright define the n-tuple that you've handed to us at the beginning. So actually, the solution in the text of this exercise needs some adjustment. Actually, the hint given is somewhat incorrect. So let's see what we should be saying here. We use a kind of Ricard paradox-like argument as from the last exercise. What we've got here is ZF is supposed to prove for all n-tuples something happens. So let's call this bit down here chi of alpha vector. For all alpha vector, and then everything here is something about alpha vector here. So this is the exists beta all the way through to here. Now we want to show chi, this holds for all alpha vectors. So again, we'll suppose that it doesn't, and we'll choose alpha vector less than sub n least for which this fails. Then take alpha vector, again, so this is this n-tuple, less than least, so that we have not chi. So let's take then the formula say phi 1 says here, alpha vector is the least n-tuple from the ordinals so that chi alpha vector fails. Okay. So we're supposing that indeed chi alpha vector does fail for this least choice here. So phi 1 alpha vector is true in V. So we can find by the reflection theorem some delta that reflects at the same time both phi 1 and psi. So by the reflection theorem, find some sufficiently large delta well, some V delta, which reflects both phi 1 and the psi that's embedded in here. And these are both formulae with free variable V0, so they're conjunction. It's a formula with free variable V0. So phi 1 of alpha vector is true in V, and delta is such that it reflects psi with V delta there. Okay, so now we have in V delta phi 1 holds. So V delta thinks this is the least tuple such that chi alpha fails. And also we have that psi is in fact actually for this V delta reflecting for psi. But this then gives us a definition over V delta of alpha vector, just as we had in 416. This gives us an outright definition of alpha vector over the structure V delta here. So whereas we thought this was the least thing in which chi alpha fails, right? I've now got a definition over V delta, right, of this alpha vector here, so that both phi 1 holds of this alpha vector here, and psi is reflecting over V delta. Together with the V delta is reflecting for psi. And so we have these two things together about delta. So in other words, delta satisfies this. Alpha vector is directly outright definable over V delta, right? And V delta is reflecting for psi. So this is a contradiction, right? Hence, we do not have, right, the chi fails on this alpha vector. Right? So that finishes this here. So from this, we can actually get our final theorem. I want to have that Z is ordinal definable is expressible by a single formula in ZF here. So we'll call it phi OD of Z, which says Z is going to be an OD. And it's just going to be, there exists a beta such that Z is outright definable over V beta. So again, this is just now a formula about definitions over a V beta. So this actually is what we called OD star earlier on. So going back to OD star, the class of set Z satisfying this here. So OD star is contained in OD. Right, so we look at the other direction here. Suppose Z is in OD. And this is then the unique set. Satisfying some formula. Phi of, for example, V0 with alpha 1 up to alpha M. So by the exercise 417 we just did, there's a beta larger than all of these, larger than the alpha I, with the vector of alpha I here definable, outright definable over V beta. And V beta reflects the formula phi. So it does these two things at the same time. And we'll assume this is large enough, so of course that Z is in V beta. here. Okay, so then, okay, phi z alpha 1 up to alpha m minus 1 here defines exactly z here in V beta. So now we've got, as it were, two definitions. We've got the definition of alpha vector over V beta by some formula or other, which doesn't require any parameters. And then I've got the formula phi defining z from that very same alpha vector. So I've got another definition here. So actually all I have to do is compose these two definitions, so to speak. Instead of phi z talking about alpha 1 up to alpha m minus 1, I find another formula, call it phi prime, right? And that phi prime will amalgamate the definition of phi with the definition of alpha vector. So I just put these two definitions together, that of alpha vector and phi, to give myself a new definition phi prime, which doesn't require the parameters. So it just puts together or amalgamates the definitions. So the definition of alpha vector over V beta with 5z alpha vector defining z over, again, over V beta. I mean, maybe this is badly put. Let me say explicitly here what I mean then. So back up, right? I need some more letters here. So let phi 2 v0 define alpha vector, which is def 0 over v beta. And then let phi prime that I'm talking about over v0 be that z, so that phi vector holds of z and d, where d is that vector so that phi 2d holds. So I have phi 2 here defining alpha vector, because alpha vector was directly definable over v beta. Here's its definition, alpha phi 2. Right? I've got phi, which defines also over v beta z from that alpha vector. So I put those two things together. So I'll let phi prime be the amalgamated definition, and it just says that z, right, that makes phi z of d true, where I plug in d as to be that vector such that phi 2d. So the only d that makes this true is the alpha vector. So hence, now z here then is definable directly over v beta. using phi prime. So this puts the Z right here that we took in OD, right, into OD star. In other words, Z is one of these guys over here. Hence Z is in OD. So OD equals OD star. Right? And that finishes the theorem. So this shows that this more informal definition here, which talked about truth of formulae in V, right, can actually be expressed in this formally correct way, just talking about definability over various V betas. So this then is a genuine definition in set theory. So next time we will look at the various properties of this OD class here.